my name is Ke Yu, and I'm an engineer from the Metal ecosystem team. Today, it's my pleasure to introduce Metal CPP. We created Metal CPP for anyone who uses C++ and wants to build Metal applications for Apple platforms. Metal CPP is a low-overhead library that connects your C++ applications to Metal. First, I'll start with an overview of what Metal CPP is and how it works. And then I will cover some details about the life cycles for Objective-C objects. C++ and Objective-C handle life cycles a bit differently, and I'll show you how to handle those differences. Xcode and Metal CPP have some great utilities that can help you manage the object life cycles in your apps. And finally, I'll show you how to integrate C++ code with Objective-C classes. So here's a look at Metal CPP and how it works. Metal is the foundation for accelerated graphics and compute on Apple platforms, enabling your apps and games to tap into the incredible power of the GPU. It was originally designed using the powerful features and conventions offered by Objective-C. But if your code base is in C++, you may need something to bridge between your code and Metal's Objective-C code. Introducing Metal CPP. It serves as a hub between your C++ application and Objective-C Metal. With Metal CPP in your application, you can use Metal classes and functions in C++, and Metal CPP can help you call Objective-C functions in runtime. Metal CPP is a lightweight Metal C++ wrapper. I say it's lightweight because it's implemented as a header-only library with inline function calls. It provides 100% coverage of the Metal API by implementing a one-to-one mapping of C++ calls to Objective-C APIs. To do this, Metal CPP wraps parts of the foundation and core animation frameworks. It's open-sourced under Apache 2 license, so you can modify the library and include it to your applications easily. Metal CPP uses C to call directly into the Objective-C runtime. This is the exact same mechanism that the Objective-C compiler uses to execute Objective-C methods. So this wrapper introduces little overhead. Since Metal CPP implements a one-to-one mapping of C++ to Objective-C calls, it follows the same Cocoa memory management rules. I will discuss this in more detail later. This one-to-one mapping also allows all of the developer tools to work seamlessly, including GPU frame capture and the Xcode debugger. These are the series calls necessary to draw a triangle with Metal CPP. If you are familiar with C++, it's a good time to learn Metal because you don't need to worry about language syntax. If you've already used Metal with Objective-C, in terms of function calls, there's very little difference between the Objective-C interface of Metal and Metal CPP. I am going to demonstrate how easy it is to use Metal CPP. First, I create a command buffer, which I will fill with commands for the GPU to execute. I can simply use the raw pointer in C++ as a mapping to ID in Objective-C. I can create a random command encoder and write random commands with the command buffer. The C++ function, random command encoder, and the Objective-C method, random command encoder with descriptor, are the same. The only differences are the name conventions of the languages. I then set a random Python state object which contains the vertex and fragment shaders and various other rendering states. Then I encode my draw call to render a single triangle. Then I indicate that I've finished encoding random commands. I present the drawable so the triangle is displayed on screen. Finally, I commit my command buffer. This tells the GPU that it can begin executing my commands. Obviously, Metal CPP and Objective-C Metal are almost the same. You don't need to worry about language syntax now with Metal CPP. You can directly look into the Metal documentation to learn the concepts and usage of Metal. You may have already played with this deferred lighting sample before. We now provide a new version of this deferred lighting sample which uses Metal CPP. We hope this can help you learn how to code with Metal CPP in practice. I'm also excited to introduce a series of incremental C++ samples that introduces the Metal API and shows you how to accomplish different tasks with it. So now that you know a little bit about Metal CPP, how do you actually use it? We published Metal CPP last year. Here's the webpage where you can find the downloads and instructions. Let me show you the steps you will need to take. After downloading Metal CPP, you should tell Xcode where to find it. Here, I put Metal CPP under the current project. Then, you'll need to set C++ 17 or higher as the C++ language dialect. Next, add 3 frameworks to the project: Foundation, Quartz Core, and Metal. Now there's only one thing left to do before using C++ interfaces of those frameworks. There are 3 headers in Metal CPP. Since Metal CPP is a header-only library, you'll need to generate their implementations before importing the header files. To do this, define 3 macros: NS private implementation, Z private implementation, and MTL private implementation. If you're interested in what Metal CPP does with the macros under the hood, please check out header bridge files in Metal CPP folder. You can use the headers separately or put them in a single header. You can import the header files whenever you need them, but remember, do not define the NS, CA, or MTL private implementation macros more than once. Otherwise, you may cause duplicate definition errors. To use Metal CPP effectively, you will need to know Cocos memory management rules, how to use the great utilities that can help you manage object lifecycles, and how to design your application architecture when you interface with other frameworks. I'll start with object lifecycle management. During your application's operation, you typically need to allocate and release memory. You also need to manage command buffers, pipeline objects, and resources. To help manage this memory, Objective-C and Coco objects include a reference count. This is also present in Metal CPP. Reference counting helps you manage your memory. Using reference counting, all objects contain a retain count property. Components in an app increase the count to keep objects interacted with alive and decrease it when they are done with them. When the retain count hits 0, the runtime deallocates the object. There are 2 types of reference counting in Objective-C. One is called manual retain release, MRR. The other is automatic reference counting, ARC. When compiling code with the ARC feature, the compiler takes the references you create and automatically inserts calls to the underlying memory management mechanism. Metal CPP objects are manually retained and released, so you'll need to understand Cocos conventions to know when to retain and release objects. Unlike creating objects in C++, Metal CPP objects are neither created with new nor destroyed with delete. With Cocos conventions, you own any object you create with methods starting with the alloc, new, copy, mutable copy, or create. You can take ownership of an object using retain. When you no longer need it, you must relinquish ownership of an object you own. You can release it immediately or release it afterwards. You must not relinquish ownership of an object you do not own, as you risk a double free. Next, I will walk through an example of these Coco conventions. In class A, a method uses alloc to create an object and init to initialize this object. Remember, never call init on an object twice. Class A takes the ownership and is responsible for deallocating it. Now the retain count for this object is 1. Next, Class B uses retain to get the object and takes ownership of this object. So far, I have 2 objects that share the ownership of this object represented by the orange cube. The retain count increases by 1. Class A doesn't need this object anymore, so Class A should manually call release for it. As a result, the retain count decreases by 1. Now, only Class B owns the object. Okay, finally, Class B wants to release this object too. Now the retain count is 0, so the runtime frees the object. Here's a situation where a method in class B returns an object. You still need this object in the rest of the programs. In other words, you want to relinquish ownership of an object in the method in class B, but you don't want it to be deallocated immediately. In this case, you should call autorelease in class B. The retain count is still 1 after you call autorelease, and thus you can still use the object later. Here's the question. Since class B does not own this object anymore, who is responsible for deallocating it? The Foundation framework provides an important object called the autorelease pool. The autorelease API puts the object into an autorelease pool. Now, the autorelease pool takes the ownership of the object. The autorelease pool decrements the receiver's retain count when the autorelease pool is destroyed. You are not the only one who can create autoreleased objects. Metal creates several autoreleased objects as parts of its operation. All methods that create temporal objects add them to autorelease pools by calling autorelease under the hood. It is the autorelease pool's responsibility to release them. In other words, with an autorelease pool, you can code in a more elegant way. You can have an autorelease pool for the main application. We also encourage you to create and manage additional autorelease pools at smaller scopes to reduce your program's working set. You also need autorelease pools for every thread you create. Here's an example showing how to use an autorelease pool and autoreleased objects. In this sample, an autorelease pool is created by ilock, which means you take the ownership and it should be manually released. Now we have an autorelease pool. As we discussed in the beginning, you should create a command buffer. It's not created with alloc or create, so you don't own it. Instead, it's an autoreleased object created by Metal. This command buffer will be put into the autorelease pool. It's the autorelease pool's responsibility to deallocate it. You can use it as you wish until you release the autorelease pool. Then you need to create a random path descriptor. This random path descriptor will be put into the autorelease pool as well. Same to run the command encoder. It's also an autorelease object created by Metal. Don't forget this current drawable object. It will be put into the autorelease pool too. At the end of the piece of code, I use ppool release to release the autorelease pool. Before being deallocated, the autorelease pool releases everything that it owns. In this case, it releases the command buffer, random path descriptor, run the command encoder, and current drawable. Then the autorelease pool is released. So far, you got to know COCO's conventions, autoreleased objects, and autorelease pools. It's important to correctly manage object lifecycles to avoid memory leaks and zombie objects. And we have great tools to help you avoid and debug these issues. I will focus on two utilities, NS Shared Pointer and NS Zombie. NS Shared Pointer is a new utility that can help you manage the object lifecycle. You can find it on the Foundation framework in the Metal CPP folder. Notice that it is not exactly the same as standard shared pointer. So there's no dependency on the C++ standard library and no extra cost on storing the reference count. Here's what NS Shared Pointer is like. Transfer and retain functions clearly express the intent of consuming an object. Transfer creates a shared pointer without increasing the pointee's reference count, effectively transferring ownership to the shared pointer. The retain function sends a retain to the passing object. Use this function to keep alive objects that are in autorelease pools and to express that the pointer's owner has a vested interest in the pointee's lifecycle. You can access the underlying object as expected via get and via the arrow operator. Shared pointer copy, move, construction, and assignment work as expected. With copy increasing the retain count, moves are fast and do not affect the retain count in the general case. Shared pointers always send exactly one release to the pointee on destruction. You can avoid this if you want by calling the detach function. Going back to the top, it's important to know the differences between creating a pointer by transferring or retaining it. So for transfer pointer, suppose I have an MRR object with a reference count of 1. After I pass it to the transfer pointer function, the shared pointer takes ownership of the object, but its retain count doesn't change. When the pointer goes out of the scope, the shared pointer's destructor runs and calls release on the MRR object, which decrements the retain count to 0. Another function is NSRetain pointer. When you want to avoid deallocating an object because you want to use it later, you should use NSRetain pointer. Suppose we have this MRR object. The retain count is 1. After we pass it to the retain pointer function, the retain count increases by 1. After running off the scope, this retain pointer calls release for this MRR object, so the retain count is 1. In general, NSTransfer pointer takes the ownership of an object for you, but NSRetain pointer helps you retain an object when you don't want it to be deallocated. When you pass an object to these two functions, NSTransfer pointer doesn't change the reference count, but NSRetain pointer increases reference count by 1 as it calls retain for you under the hood. The destructor of these two functions both call release for the passing object, and therefore reference count decreases by 1. If the reference count hits 0, the object will be freed in runtime. Here's an example of NSTransfer pointer. When I talked about the render path which I drew a single triangle, I needed this render pipeline state. Here are the calls to create a render pipeline state object. These are the attributes that a render pipeline descriptor needs. According to Cocos conventions, since this course starts with new and alloc, I own these objects, so I need to call release for these objects. With NSShared pointer, I don't need to call release for those MRR objects because NSShared pointers takes ownership of these objects. So here, I pass write pointers to the transfer pointer function. After doing that, there's no need to call release as I did in the previous slide. If you are familiar with Arc, you may find that MRR used with NSShared pointer is similar to using Arc. You may encounter use after-free bugs when handling memory manually. They occur when you're trying to use an object which has been already released. NSZombie is a good way to check for those bugs. When use after-free bugs occur, it triggers a breakpoint and provides you with a stack trace. You can enable zombies very easily with an environment variable. Just set NSZombie enabled to yes. Or, if you are using Xcode, you can enable zombies in a scheme. Here's how it works. I want to create a new render pipeline state object with the same render pipeline settings. So, in this new render pipeline state function, I reuse the pDescriptor object. After clicking on Run, Xcode triggers a breakpoint and shows me the stack trace. That means I got something wrong. What's the problem? Maybe NSZombie can help here, so I enable NSZombie in Scheme. When I run the program again, NSZombie triggers a breakpoint. I get something new in the console output. Message sent to the allocated instance. Oh, I reused an object that I have already released, and it's the render pipeline descriptor. So I need to use this render pipeline descriptor before calling release. By doing that, I fixed the problem. More tools and details are covered in this year's talk. Profile and optimize your game's memory. For example, you can learn how to track retain count in allocations in instruments. Feel free to check out other tools on Apple platforms. You will find out that they can help you debug your game and improve performance. Now you know how to manage object lifecycles in Metal CPP. But you may still need to interface with other frameworks like Game Controller and Audio. They are still in Objective-C. How can you interface with those APIs and design an elegant application architecture? Say you wrote a view controller in Objective-C, but you wrote a renderer in C++ with MetalCPP. You need to call renderer methods like draw from the view controller. The challenge here is to nicely separate the two languages but have them work together. The solution is to create an adapter class which calls C++ from Objective-C files. By doing this, you can focus on Objective-C or C++ in files where you implement features. For example, I can create a renderer adapter class in Objective-C, and down in the implementation, I add an Objective-C method so that I can call it directly from the view controller. Inside of the interface, I declare a C++ pointer to a renderer object. Inside the body of the method, I directly call the renderer C++ method. This method needs to pass the MetalKit view as a C++ object into the draw method, so it casts the view as a C++ type by using the bridge keyword. I will talk more about this cast later. In contrast, you need to call mtkview, which is written with Objective-C, in renderer, which is written with C++, is challenging as well. Similarly, the solution is to create an adapter class. With this class, in C++ files, you can call Objective-C methods using C++ interface. For example, I can create a view adapter class. I write the interfaces in C++, so in the renderer class, I can call those C++ view methods easily. While in the implementation, I call Objective-C methods from mtkview, including current drawable and depth stencil texture. You may notice there are some bridge keyword here. I use them to cast between MetalCPP objects and Objective-C objects. As you learned in the beginning, MetalCPP objects are manually retained and released, but objects created by Objective-C use automatic reference counting. You need to move objects from MRR to ARC and from ARC to MRR. Here are three types of bridge casting which can help you cast between Objective-C and C++. They can also help you transfer ownership. Bridge casting casts between Objective-C and MetalCPP objects. There's no transfer of ownership between them. Bridge retained casting casts an Objective-C pointer to a MetalCPP pointer and takes the ownership from ARC. Bridge transfer casting moves a MetalCPP pointer to Objective-C and transfers the ownership to ARC. Going back to the problem, you need to cast between MetalCPP objects and Objective-C objects. If there's no transfer of ownership, you can use bridge cast. If you want to cast from MetalCPP to Objective-C objects and transfer the ownership to Objective-C, you should use bridge transfer cast. If you want to cast from Objective-C to MetalCPP objects and take the ownership out of ARC, you should use bridge retain cast. Here's a case when I have to use MetalKit to leverage the asset loading code. That means, in my C++ application, I need a texture as a MetalCPP object, but it is created by Objective-C methods. I need the ability to transfer ownership out of ARC so I can manually release it. And in this case, I need to pick bridge retain cast. I have this C++ function that loads a texture from the catalog, and I want to return a MetalCPP texture. But inside, I'm calling some Objective-C functions in MetalKit. I need to define the options that the texture loader needs. Then, I create a texture loader by calling an Objective-C method from MetalKit. With that loader, I can create a texture object and load the texture from the catalog. This method is also an Objective-C method from MetalKit. Now, I have an Objective-C type texture. I need to cast it to the MetalCPP object and take it out of ARC. With these steps in mind, it's time to code, and I'll show you how casting works in practice. First step is to define the texture loader options that a texture loader needs. I can safely cast the Metal CPP storage mode and usage to the Objective-C type, as Metal CPP type-defined them to the same values. Here, I create a texture loader. I have a device that is a Metal CPP object, and I need to pass it to the initWithDevice method. Because the Metal CPP object is an Objective-C object, I can cast it like a toll-free object. There is no transfer of ownership. Now, I use the texture loader options and the texture loader to create a texture. And I want to return the loaded texture as a Metal CPP object. So I need to take it out of ARC and cast it to the corresponding pointer type. This is done with a bridge retain cast. After this, I can use this texture as any Metal CPP object. I'm responsible for releasing it. In this section, I provided an adapter pattern which can help you handle 2 different languages in your program. I also showed how to interface with Objective-C and C++ with 3 types of cast. To summarize, Metal CPP is a lightweight and very efficient Metal C++ wrapper. I talked about how to manage object lifecycles when using Metal CPP, how to interface with Objective-C in an elegant manner, and how our developer tools can help you debug. Download Metal CPP and play with all the amazing samples now. See what you can create with Metal. We look forward to seeing your C++ applications running across all Apple platforms. Thanks for watching.